And we're back. Welcome back and happy Tuesday. Today we will continue on with our discussion of descriptive statistics with an emphasis for today on measurements of dispersion for distribution. But before we begin, some administrative bits. The reading has changed by February 5th. Please make sure you've read up through and including section 8.3 in the text, third edition, pages 230 through 239. Homework number 1 has been out since last week. It is due on Thursday, the 4th of February, 2021. So where we last left off, we talked about how you compute the sample median. And we said that you either take the middle order statistic, or if your number of samples is odd, but if your number of samples is even, you take the two middles and calculate the midpoint. So let's say we have n many observations, and in this case n is 30, it is even. And if it is odd, you take n, add 1, divide by 2, and you take the n plus 1 over 2 smallest observation. Of course, this case is even. We have 3 rows of 10 for 30 numbers, and you take the midpoint between the two middles notionally, which is the n over second and the n plus 2 over second observation. So we have our observations here sorted in non-decreasing order. So there's the first row, there's the second row, the third row. So n is 30 in this case. So n over 2 is the 15th. So that's 10, 11, 12, 13, 14, 15. That's the 15th smallest observation. And you take n plus 2 over 2. So n plus 2 is 32. Divide by 2, that's 16. So that's the 15th, there's the 16th. And then you take the midpoint. The midpoint between 42 and 43 is 42.5. And that's our result. All right, so let's go to measurements of dispersion. Now, we can generalize this notion of the median. We said the median splits a distribution into two equal parts, and those equal parts, if you were to take the area under the curve for the probability distribution split in two parts, equal parts, each one would have a probability of 0.5, 50%. But we enterprise in many cases to look at more than just halving the probability mass. So let's consider arbitrary partitions of a distribution. You can partition the distribution, for example, into 4 parts, and that's depicted in this figure. Here we have the first part by probability mass, 25%, the second part, the third part, and the fourth part. We could divide up into 10 parts, or some other arbitrary percentage, p, where p is a proportion. Now, let's bring in some definitions. A so-called p-quantile generalizes this notion of the median. A p-quantile is some number, let's call it x, that solves the following. The probability that an observation, big X, that's a random variable, is less than the p-quantile x is at most probability p. So the p part for the p-quantile, that's going to be a probability, and it is the likelihood that an observation arbitrarily, a random variable x, will be less than that particular number. That probability is no more than probability p, less than or equal to p. Likewise, for p-quantile, the probability that an arbitrary observation, random variable x, exceeds that p-quantile x is going to be at most, that probability, at most 1 minus p. So that means if we were to look at our probability distribution and you have some value x and some probability distribution, well, if you were to take the area under the probability curve, the total probability mass, for all the values that are less than x, that probability is going to be at most probability p. And if you were to take all those values that random variable big X can take on, that might be above or greater than that p-quantile, well, that probability is going to be at most 1 minus p. The sample p-quantile is the sample version of the p-quantile. And the sample version, formally, is the number of observations, because remember it's a sample, exceeding at most 100 times p, and you read that as a percentage of the sample, and precedes at most 100 times 1 minus p. So that means if you have a set of samples, x1, x2, x3, dot, 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 up to and including xn, well, it's in non-decreasing order, right? And the sample p quantile is some value. Let's call that xq for quantile. And it's the number that exceeds, meaning that it's bigger than, no more than 100 times p as a percentage. And so if p were, for example, 70 or 0.7, that would be 100 times 0.7 or 70%. And that particular value in the case of p is 0.7 would be would exceed no more than 70% of all of the observations, all of the samples. Likewise, at the same time, if you look at your sample p quantile, it's going to precede or be smaller than at most 100 times 1 minus p. So if p were 70%, 1 minus p is 0.3. So that would be 30% of the samples are greater than that sample p quantile, and 70% of your samples will be less than, or more than 70% of your samples will be less than that p quantile. So then we also have a percentile, a so-called gamma, and this is lowercase gamma. A gamma percentile is a 0.01 gamma quantile. And so when you talk about gamma, gamma is going to be a number between 0 and 100. And so if you say something is the 70th percentile, so gamma would be 70, that's the same as a 0.70 quantile. So percentile is just another way of talking about the quantile. The quantile, it's the probability, it's the proportion, and for the percentile, it is a percent. Okay, so let's look at some example places, quantiles, along the distribution. And so here we have some quantiles, and this quantile here is the 0.25 quantile. This one is the 0.5 quantile. This one is 0.75 quantile. Now, these quantiles do something special. They chop up the total probability mass of your distribution into 0.25 equal sized parts. And so because it divides your distribution up into 4 parts, it's often called quartiles. Quartiles. And so here we have the first quartile, Q1, the second quartile, Q2, and the third quartile, Q3. And the first, second, and third quartiles represent the 25th, 50th, and 75th percentile, respectively. Remember, when we said the gamma percentile, we talk about percentages per centum out of 100. And so if we're to look at the median, we said the median is preceded by no more than 50%, no greater than 50, and it's exceeded by no greater than 50%. So if we were to look as a quantile, the median is the same as a 0.5 quantile, right? It's right in the middle. And so the median we can call by different names. We can call it the 0.5 quantile. We could call it the 50th percentile, so as a proportion or as a percentage, or we call it the second quartile, Q2. So there are many different ways we can call out or describe the same statistic as far as its positioning relative to all the values we might obtain from a distribution. Okay, so let's look at some nomenclature. So when we talk about quantiles, we say Q, and we subscript it with P, that proportion. And then when we talk about the sample equivalent of the population quantile, we give it that little hat because it's an estimator. right? You can stand in place. It's over the samples. So the sample P quantile is an estimator of the population P quantile. Likewise, when we talk about the population gamma percentile, remember that is a percentage per centum out of 100. We denote that in the book as pi, which the author does. And then we can have the estimator percentile we use as a stand in place, take the replacement of, or take the place of the population gamma percentile, and that just includes a hat. So pi sub gamma hat is the sample gamma percentile, and we use this as an estimator of the population gamma percentile. So we also have the population quartiles, Q1, Q2, and Q3. We have their sample equivalent, which are estimators for the population quartiles, Q1 hat, Q2 hat, and Q3 hat. We have, as we had before, the population median, and we solve for that. And then we have the sample equivalent, which is an estimator of the population median. The sample median is M hat. And so there are equivalencies between them. If we go from the P quantile to the gamma percentile, well, we just multiply by 100 when we go from quantile to percentile. So the population P quantile, that's Q sub P, is the same as the population 100P, and that would be our gamma value. So our gamma value would be 100P, is the same as the 100P population percentile. Likewise, the first quartile is the same as the population 25th percentile, so gamma is 25, which is the same as the 0.25 population P quantile, where P is 1/4. And likewise, the third population quartile is the same as the 75th population percentile, which is the same as the 0.75 population quantile. Okay, so this is just to show you some equivalence and relationships between the different ways you can represent values that take a certain place within an ordering of the set of values you can draw from a distribution or that is in the population. All right, so we talked about spread or dispersion for a distribution last semester, and we looked at variance, and we said variance has an issue. Its units is squared, which is kind of nixing because it's hard to compare variance or cast it in the same consideration as the center of mass or the mean. And so we took the square root and got the standard deviation, and the standard deviation allowed us to express units in the same unit as the mean, median, or the measurements. And so we said that standard deviation is a measure of dispersion. It's the square root of the variance. And we said that if the variance and therefore standard deviation is smaller, we get something like this blue curve. Our probability mass is more concentrated among a smaller, broad range of values of our random variable. And if our standard deviation is larger, we get something like this pink curve, which says that the range of values we might observe for the random variable are spread out among a broader range of values. And so if we have a sample, x1, x2, x3, up to and including xn, the sample variance is s squared, that's the symbol we use for it, it's 1 upon n minus 1 times the sum, I goes from 1 to n, of xi, each measurement, minus x bar, where x bar is a sample mean quantity squared. And we get the squared term because we care about the magnitude of the difference between each measurement and the center, but we don't care about the direction. Now, this is not a typo. When we see this 1 over n minus 1, we'll talk a little bit more in subsequent modules about why that is not a typo. And so variability or dispersion is measured, in this case, from your sample between each one of the observations, each one of these xi's, where I goes from 1 to n, and the sample mean, where the sample mean, again, is our x bar that you calculate over the entire sample of size n. And s squared is going to be used as an estimator for the population variance. Now, this population variance is what we referred to last semester as the variance. Okay. And so The sample standard deviation, just like the population standard deviation, is just the square root of the sample variance. Okay, so we take our S squared, we take the square root of that, we get a statistic, a value, and we call that our sample standard deviation. And so this sample standard deviation is going to serve as an estimator for the population standard deviation. And so you could actually maybe note, if you chose to, that the sample standard deviation S is the same as sigma hat, where sigma hat is going to stand in place as an estimator for sigma. Okay. And so this sample standard deviation is going to express the dispersion of your sample that you've measured in the same units as the median, as M. And so this sample standard deviation does the same thing as the population standard deviation. It remedies the fact that the units are squared when you have the variance term. Okay. So we talked about the distribution of the sample mean previously, and we looked at its standard deviation. We call that standard error. And if you have any statistic, any estimator, theta hat, its standard deviation is called its standard error. And so let's recall then the MATLAB for the variance of the sample mean, and I'll illustrate what I mean by this standard error. So why don't we go back to MATLAB? I will meet you in MATLAB. So we're here in MATLAB, and in this experiment, we're going to take a population, that is simulated population, and the population has 100,000 members, and it's going to be a population of numbers, each one of which is randomly selected from a closed interval between 0 and 1 million. And so we'll start out with our population size, and then we'll randomly, we run it, create some samples, and we're going to sample 100,000 many times in the interval from 0 to 1 million. Okay, so if we do that, we get a vector. We continue, and we can take a look at that vector. It's just some numbers between 0 and 1 million, and there are 100,000 of these numbers. So we calculate mu, the ground truth sample, the ground truth mean of this population of numbers. And of course, I'm showing it to you, but in reality, you don't get to see this. And so this ground truth is about 499,000, which makes sense, because if you have things sampled uniformly from 0 to 1 million, the mean ground truth is going to be about halfway in between 0 and 1 million. And so we do this, and let's step. And now what we're going to do is some number of times, 2,000 many times, this is going to be num rounds, we're going to select 10 of these individuals from our population. And so the mechanism we use to select those 10 is going to be by selecting 10 many indices within our population array, and then using it to extract the values. Okay, so let's go ahead and do that. Continue. And when I extract these values, well, there's one iteration. We'll see 988,094, 19,255, and a couple others. We're going to take the sample mean, or calculate the sample mean, from our sample of size 10. So we do this, okay, and when we calculate the sample mean, that's going to be our theta hat, our x bar. Our x bar is our theta hat. It's the estimator for theta, where ground truth theta is mu, the population mean. So I do that again and again and again, and I save off all of my theta hats, and I'm going to plot the distribution through a histogram of my theta hats. But in addition to plotting that distribution, two things I'm going to calculate. I'm going to calculate the expectation of my theta hat, which is about 498, and remember ground truth is 499, it's very close. Now this is unbiasedness in action. We said x bar, sample mean, is unbiased. The expectation of it, on average, is exactly the ground truth parameter. Okay. Now we're also going to take the standard error of all of these x bars, because each of these calculations, this theta hat, the sample mean x bar, we have 2,000 of them because we do this 2,000 many times. Take a sample of 10 and compute x bar, the sample mean, and then we compute the expectation of this, or the mean, or the expectation of all of these x bars, and we compute the standard error of all of these x bars. That standard error of the x bars is called standard error because x bar is a statistic, and that's nothing more than the standard deviation of each of these, of this group of theta hats that we calculated, these 2,000 theta hats in this case. So I'm going to plot the histogram to visualize for you the distribution, and we'll see some interesting things happen. Okay, so this is the distribution, and I'm only using 20 bins. I could use a larger number if I chose to. Distribution of x bar. And so for x bar equals 2, we have a very small number. But for x bar equals about 5 times 10 to the 5, well, that says there are 272 of them. And this is the mode, or the high point of the distribution. And what I've also marked here with the triangle, I'm marking the expectation of x bar, the expectation of our sample mean. And with asterisk, I'm marking the ground truth population mean. And you'll notice the two coincide almost perfectly. And I'm writing on this graph the standard error, and you notice that the standard error is, or the standard deviation, is 90,660. Okay. So watch what happens when I increase the sample size. It's no longer going to be 90,000, it's going to get smaller. So let me make the sample size, instead of 10, let's make it 100. Okay, so let's save that. Let me clear my breakpoint, and let me just run this again. So I run it again. You'll notice the standard error of my sample mean, my x bar, is no longer 90,000 and change, it's 28,000. It got a lot smaller. So the standard error is getting smaller and smaller and smaller. Let's disperse for this sample statistic, this x bar, our theta hat, our estimator, as we increase the sample size. Okay, and so when we talk about standard deviation, absolutely we can calculate standard deviation either from the raw samples, or we can calculate standard deviation for a statistic, for an estimator. In this case, it's x bar. And when we do that for a statistic, calculate the standard deviation from the samples, we call it standard error. Okay. So let's end there. We'll meet you back in PowerPoint. So we're back in PowerPoint. And when we calculate standard error, well, what are we doing? Computing standard deviation over a set of samples, but these samples are the outcome of calculating a statistic, i.e. an estimator. Okay. And we see that the standard error gets smaller as you increase the sample size. And that's just a nod towards consistency. In the limit, as you increase the sample size, as the sample size goes to infinity, the difference, the probability that the difference between the estimator and its expectation exceeding an error tolerance goes to 0. So it gets less and less and less likely that it's going to be different from the ground truth parameter, this estimator, as you increase sample size. All right. So let's take a look at this figure. And this is an interesting figure. It looks at how reliable an estimator is, how good of a stand-in it is for the ground truth population parameter. And this is in the book, and each dot represents a different instance of our estimator theta hat, and in our case, carrying through the example, it's our x bar. And so I'll direct your attention to this upper left-hand part of the diagram. Let me set my pen, and I'll just mark that as the first figure. Now, here we see our ground truth parameter, theta, population parameter, which is the same as the expectation of our theta hat, the estimator. And each dot represents an instance, a different instance or measurement of our theta hat, of our estimator. And so this first figure represents a biased estimator that has a high standard error. Now, it's biased, meaning that it's going to prefer values for this estimator that are fairly large. And because this theta is the expectation, it is the center of all the values, or for the distribution of all the values that the theta hat can take on. So if you notice all of these values, more of the values of our estimator theta hat are on the right-hand side, right? They're larger than the expected value. And you'll notice the spread over which they are dispersed is relatively large. So this represents a biased estimator. In the same vein as we talked about unbiased, this violates that. It's biased. Okay, so let me draw your attention here to the second frame in the top hand right. This is the same graph, but this represents an unbiased estimator that has a high standard error. So a high standard error, you notice the values that theta hat, our estimator, can take on is very dispersed, but it's spread over all of the different range of values that it could take on. So we have a bunch of them spread apart roughly equidistant here, and a bunch of them spread over here, covered over there, and so forth. So this is unbiased with a high standard error. Well, it's not consistent, but it's unbiased. Here, it's biased and a high standard error, so it's not consistent. Now let's look at frame 3 in the lower left-hand corner. This is a biased estimator, so it's going to prefer some values over others, and here it's preferring the high values. We notice all the values that theta hat can take on are the large values to the right of the expected value theta. But the dispersion is relatively small. They're very tightly packed to one another. And so this represents a biased estimator, so it would fail this particular statistic. This estimator would fail that test of unbiasedness, but it's consistent, right? Low standard error. It's concentrated among a small set of values. Now, this last frame 4, that is what is perfect, what you're after with some estimator. It's both unbiased, meaning that it's balanced throughout all sides, above and below our expected value, and it has a low standard error. The dispersion is small. And so an estimator that exhibits this quality in frame 4, unbiased, passes that unbiased test, low standard error, passes the consistency test, well, this is a very good replacement. Now, what can you do if you have something that doesn't satisfy the bias test and consistency as we see in frame 4? Well, you can try to remedy that. And there are a bunch of ways that you can do this. All right. But if you know how it's biased, or you know about its inconsistency, well, you can also try to remedy that as well. Okay. So there are other ways in place to measure dispersion. We talked about the sample mean, we talked about variance, the standard deviation, and all of those are sensitive to outliers, meaning an extreme observation, one that's very big or very small relative to the others, can significantly affect our sample mean, x bar, as well as our sample variance, s squared. And the interquartile range, like the median, is not very sensitive to outliers. They don't change in value very much if you add an extreme value, either one that's too big or too small relative to the others. And so the other way we're going to use to measure dispersion that doesn't have this brittleness that s squared, our sample variance, has, and s, our sample standard deviation, has, is the interquartile range. And the interquartile range is nothing more than the difference in value between Q3, the third quartile, and Q1, the first quartile. And so we said again, the first quartile is at the 25% point for the total probability mass under the distribution curve. And the third quartile is at the 75% point. So there's the third quartile, there's the first quartile. And so literally take whatever the value is for that value x, which is Q3, and y, which is Q1, and we just subtract. That's our interquartile range. And so if a distribution is not very dispersed, well, what's going to happen? Here's Q1, here's Q2, here's Q3. Well, the difference between Q1 and Q3 aren't going to be very big. Take, for example, a distribution that is very dispersed. Here's Q2, here's Q3, here's Q1, and you notice the difference between Q1 and Q3 is very large. Okay, and so interquartile range is another measurement of dispersion that we can use, and it is not as brittle to outliers as the sample variance as well as the sample standard deviation. And so you can estimate the interquartile range using the sample interquartile range, which is nothing more than the difference between the sample third quartile and the sample first quartile. So when we talk about interquartile range, we refer to populations, but we specifically talk about sample interquartile range when we connote in our notation this hat. It says it's an estimator. So IQR hat is an estimator for IQR. IQR, the population interquartile range, is Q3 minus Q1. IQR hat is Q3 hat minus Q1 hat. Okay. It just so happens that 99.3% of the population of values that you observe fall 1.5 IQRs interquartile from the quartiles. That means to the left of Q1, smaller than the first quartile, or to the right of Q3, larger than the third quartile. And so suppose you had a sample interquartile range, IQR hat. 99% of the population values, we said, falls within 1.5 IQR from the quartiles, the upper and the lower. So 1.5 IQR, whatever the interquartile range is, that value for sample IQR, we multiply by 1.5, and we know that any value within that range above and below 1.5 IQRs is going to represent 99.3%. So that means it gives us a way to detect outliers, values that are too small or too big, and we can use this sample IQR as the basis of rejecting measurements. So that could be things like heart measurements, or it could be temperature measurements, all sorts of things. How do you reject outliers? You can calculate your 1.5 IQR, you get a new example, test it, and then you include it in the new date in your data, and then you recalculate your IQR, new sample comes, test it, and keep going. So let's take an example, and in this example we have a bunch of measurements, and these values are sorted in non-decreasing order, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And we said the quartile is the number that exceeds at most 100p% of our values. So let's go ahead and calculate our quartiles. And so the quartile is that p is 0.25, so we have 0.25 and 0.75 as Q1, it's 0.25, and Q3 is 0.75. So the first quartile exceeds at most 25% of the measurements, that would be 4. The second quartile exceeds at most 50%, so 50% of 12 is 6, that would be 7. The third quartile exceeds at most 75%, 75% of 12 is 9, so we mark 10 as the 75th percentile. Okay, so now we call this Q1, has a value of 4, Q2 has a value of 7, Q3 has a value of 10. All right, so now the IQR hat, the sample interquartile range, is 10, that's Q3, is equal to 10, Q1 is equal to 4, so the IQR is 10 minus 4, which is just 6. Okay, and so knowing that we have an IQR of 6, we say, okay, well, 1.5 IQR, that's 1.5 times 6, that's just 9. So given 1.5 IQR hat is 9, well, we know that Q1 minus 1.5 IQR, well, that's going to be 4, which was Q1, minus 9, which is 1.5 IQR, that's negative 5. Likewise, Q3, our third quartile, plus 1.5 IQR, that's 10, that's Q3. 1.5 IQR is 5, that's 10 plus 9 is 19. So what does this mean? Well, that means that 99.3% of all the population values that we're going to observe from whatever system we took samples from that gave us these values, 99.3% of the population of the values is going to fall in the range between negative 5, which is out on the left here, and positive 19, which is out on the right over here. And so any value that you get that is less than negative 5 or greater than positive 19, that's considered an outlier because it doesn't represent the majority. It only represents 0.7% of the values that you could observe. And so you can use this in real time to reject outliers for all sorts of types of measurements. And it gives you a very quick way of calculating it. And if the sample is done well enough, it can stand in as a very good replacement for the population IQR. Okay, so that's all I had to say for today. Again, please make sure you're working on the homework. And as usual, please stay healthy, stay safe, and I will see you all on Thursday.